Magandang araw po sa ating lahat. Ako po ay naatasang i-discuss sa inyo ang tungkol sa Doppler Effect. I am Michael C. Roque, Teacher 3 of Orani National High School, Parang-Parang. The Doppler Effect is covered under Learning Competencies GP 12 MWS 37. Relate the frequency, source-dependent, and the wavelength of source with the motion of the sound and the listener. Our session objectives are define Doppler effect and calculate Doppler effect related problems. Let's see how far you know about Doppler effect. What is radar? Do you have any idea? How about sonar? Yes, you're right. Radar is radio detecting and ranging. How about sonar? Comment down below. Yes, I see. Sound navigation and ranging. Now let us determine whether you have a prior knowledge about Doppler effect. So this is only a true or false question. Write up on your comment and T if it's true, F if it's false. Number 1 question. Frequency and pitch is the same. Comment your answer now. Okay, that's it. Yes, the answer is F, that is false. Question number 2. Frequency emitted increases as the sound source moves towards the observer. Is it true or false? Okay, the answer for that question is false. It is the perceived frequency that is increasing, but the emitted frequency stays the same. Okay, number 3 question. Try more. There is no Doppler effect if both the source and the listener are stationary. True or false? Okay, is it comment there? Yeah? Correct. That is true. If the observer and the sound source is both stationary, there is said to be no Doppler effect. Doppler effect is defined as the relative change in the observed frequency heard by the observer relative to the motion of either the source or the listener. Doppler shift takes place when the sound source and the listener are both moving either towards or away from each other. By then, if we try to look at this one, this phenomenon was actually discovered by Christian Doppler, 1803 to 1853. He is an Austrian physicist who discovered the phenomenon known as Doppler effect. As you observe from the animation, as the sound source moves towards the observer, the frequency increases as it was heard by the stationary observer, while on the other end, the sound heard decreases. Let us have the case 1.1. The observer moves towards the source. As you see, as the observer approaching the source, the pitch heard by the observer increases. The sound increases. But the wavelength decreases because it is compressing as you move towards the source. Now, let us consider the equation F sub O is equals to F sub S multiplied by the quantity V plus V sub O over B. So let us identify one by one. F sub O is the observed frequency, while F sub S is the source frequency, while B is the velocity of sound in air, and B sub O is the observed velocity, while B sub S is the source velocity. Now let us apply. Let us analyze and solve this problem. A man is running on a road with a velocity of 5 meters per second, approaching toward a stationary ambulance, which generate a sound with a single frequency of 420 Hz. Further, the sound speed is 340 meters per second. Calculate the frequency of the sound heard by the man. Okay, of course, we need to write down the given. So what are the given on this problem? The given are the frequency source, which is the Fs is equals to 420 Hz. The velocity in the air, which is 340 meters per second. The observer velocity is 5 meters per second. The missing variable is the FO. Now, we're going to use the formula FO is equal to Fs times the quantity V plus B sub O over B. So we're going to substitute the value from our given. So let us have FO is equals to 420 Hz, that is the Fs, multiplied by the quantity 340 meters per second, that's the velocity in the air, plus 5 meters per second, that is the velocity of the observer towards the source, over 340 meters per second, close quantity. Following the PEMDAS rule, so we're going to add, divide, and multiply. So 340 plus 5, that is 345, divide 340. Cancel all unit meter per second. Multiply it by 420 Hz. So we have now the product 426.2 Hz. May fast? Okay lang po ba kayo dyan? Kaya pa? Mabilis po ba? Comment nyo lang po kung mabilis o sakto lang po. Tutuloy na po ba ako sa susunod na case? We have case 1.2. The case 1.2, the observer is moving away from the source. In this case, the wavelength as the observer move away from the source is stretching. And let us have now the formula. The formula is a quite derivation from the first one. In our first formula, we have the positive velocity of the observer. In this case, we have the FO is equals to Fs multiplied by velocity minus velocity of the observer over the velocity. So let us again define. FO is the observed frequency. Again, Fs is the source frequency. V is the velocity in the air. And B sub O is the observed velocity, while Bs is the source velocity. Now, considering this formula, let us apply it on our second problem. The same problem, only on different situation. Instead of moving towards, it's now moving away from the source. Let me read it for you. A man running on a road with a velocity of 5 meters per second move away from a stationary ambulance which generates sound with a single frequency of 420 Hz. Further, the sound speed is 340 meters per second. Calculate the the frequency of the sound heard by the man. So what would be the perceived frequency in the man's ear. So first procedure, let us write the given. What are the given? Yes, you're right. That is 420 hertz. This belongs to Fs. What's more? Yes, that's 340 meter per second. That's the velocity in the air. Another, yeah, the 5 meter per second. What is missing? Very good. That is the frequency observed by the moving away observer. Now, let us write the formula. Our formula then is FO is equals to Fs multiplied by the quantity B minus B sub O over B close parenthesis. By substituting the value, we will obtain FO is equals to 420 hertz times the quantity 340 meter per second. Now this time, instead of adding, we have the subtraction. We're going to minus 5 meter per second, and then we're going to divide it with 340 meter per second. So that is 340 minus 5, that is 335, divide 340, then multiply it by 420 hertz. So our product is 413.8 hertz. We will observe that there is a decrease in the perceived frequency. The explanation to that is simple. Because the observer is moving away from the source. Okay pa po ba kayo dyan? Kaya pa. I will proceed on the third case. The third case is moving toward each other. Let's put it into this perspective. Two cars approach each other at 50 meter per second. It means the first car and the second car both having a velocity of 50 meter per second. When one car starts to beep its horn at a frequency of 475 hertz. What is the wavelength of the horn as heard by the other driver when the sound velocity is 343? In our third case, it is Doppler shift. It means the two objects are moving towards each other. Then the given are the velocity in the air, which is 343 meter per second. The velocity of the source, which is 50 meter per second. And the velocity of the observer, which is also 50 meter per second. And of course, the frequency emitted by the source is 475 hertz. What is missing here is the observed frequency and the wavelength. So we have here a two-step problem. So for our formulas, we have FO is equals to Fs multiplied by the quantity B plus B sub O over B minus B sub S. That is for the perceived frequency. For the wavelength, we have the lambda is equals to V over F, where of course, the lambda is the wavelength, and the B is the velocity, and the F is the frequency. Now, let us substitute. First, for the perceived, or the FO. FO is equals to 475 hertz multiply by the quantity 343 meter per second plus 50 meter per second. Divide 343 minus 50 meter per second. Following the MDES rule, then if we multiply the sum and the quotient with 475 hertz, we will be having 637.1 hertz. Do you have the same answer with me? Comment yes. You have a violent reaction? Kindly write it down. Now, the second problem here is the wavelength. What is the wavelength? Since our velocity, or the v, stands for the velocity in the air, that is exactly 343 meters per second for this case, divide 637.1 hertz. Then, we have hertz is equals to cycle per second, so that would be cancelled second. So what the unit left is meter. So that is 343 divide 637.1, that is 0.54 meter. Do you have the same answer? Okay, let's proceed on case 2.2. In case 2.2, if the source and the observer are moving away from each other, I will use the same example. Two cars moves away from each other at 50 meters per second. When two cars starts to beep its horn at a frequency of 475 hertz, what is the wavelength of the horn as heard by the other driver when the sound velocity is about 343 meters per second? It's quite similar with our first problem, only the case is moving away. Our 2.1 case is moving towards each other. This time, they are moving apart. So again, the formula, before that, let us first have the different given. So what are the given here? We have there the velocity of the source, that's 50 meters per second. The velocity of the observer, that is 50 meters per second. The frequency of the source, that's equivalent to 475 hertz, while the velocity in the air is equivalent to 343 meters per second. Now, let us proceed. What equation is to be used? Okay, for our formula, we have FO is equals to Fs multiplied by the quantity velocity minus velocity of the observer divide velocity plus velocity of the source. And for our second problem, for the wavelength, again, lambda is equals to V over F. Now, let us proceed to the substitution. For the perceived frequency, or the FO, is equals to 475 hertz multiply by the quantity 343 meters per second minus 50 meters per second divide 343 meters per second plus 50 meters per second. So that is 293 divide 393 times 475 hertz. So the product is 354.13 hertz. Now, after getting the observed frequency, we're going to proceed now. What would be the wavelength of this perceived frequency? So again, the velocity in the air is 343 meters per second. Let us divide that with the calculated observed frequency, which is 354.13 hertz. So we have 0.97 meter. Now, that will be our try this wavelength. I'll be giving you ample time. We have two problems here. Get a piece of paper. Try to answer problem 1 and 2. I'll be giving you around 10 minutes. I think that would be sufficient enough. We're going to answer problem 1 and 2. Okay? As you try to answer this one, I will play a song for you. Okay, that's it. I think you got it correctly. Let's see. Comment down below your answer. For number 1, what is your answer? How about number 2? Let's see. These are the answer. For number 1, that is 484.24 Hertz. And for number 2, that is 805.65 Hertz. For the practical usage of Doppler effect, these are just few. Doppler effect is used by the meteorologists to track storm. So that's very useful. The second one is the doctor used the Doppler effect in hospital to diagnose heart problem. And number 3, it was actually used in traffic. Traffic police make use of Doppler effect, a radar gun, to check whether the speed of an oncoming vehicle is overspeeding. I think na-experience nyo yan. From one end, may bumaril sa'yo na speed gun, at the other end, ikaw ay magbabayad ng ticket. If you experience that, that is because they use the Doppler effect. Madami pa pong usage ng Doppler effect, pero I just want to give this 3. For more details, kung gusto nyo pong mag-research, pwede nyo pong hanapin ang Doppler effect by bjjuice.com, at pwede rin po yung Conceptual Physics by Paul Hewitt, General Physics 1, of course yung Physics 4 ni Narvasa Valdez. Ayan po yung aking mga source. Pwede nyo pong hanapin yan at pwede nyo pong i-consult. Maraming salamat po sa lahat ng nakinig at nagbigay ng oras. Thank you very much. Pagpalain po tayo.